Hi, today I will be doing a presentation on WebRTC. I'm going to talk about the technology behind it, its history a little bit, and I'm finally going to finish off with a little demo that I put together. I hope you enjoy it. WebRTC is a technology which enables web applications and sites to capture and optionally stream audio and/or video media, as well as to exchange data between browsers without requiring an intermediary. It is a free open source project. WebRTC is a state-of-the-art media stack that achieves functionality via easy-to-use APIs, providing the building blocks for high-quality communications on the web with network, audio, and video components. Audio and video communication is facilitated by allowing direct peer-to-peer communication, which eliminates the need to install plugins or download native apps. WebRTC is nothing short of a new communications platform that allows developers to build a single app that can run across most modern browsers. WebRTC serves multiple purposes and overlaps substantially with the Media Capture and Streams APIs. Together, they provide powerful multimedia capabilities for the web, including support for audio and video conferencing, file exchange, identity management, and interfacing with legacy telephone systems by sending DTMF signals. In fact, over 1 billion people worldwide are presently using a WebRTC-enabled browser. Supported browsers and platforms currently include Google, Firefox, Opera, Safari, Microsoft Edge, Vivaldi, Brave, Android, BlackBerry, and iOS. The WebRTC project has received support from Google, Mozilla, and Opera. WebRTC is being standardized on the API level by the World Wide Web Consortium, W3C, and at the protocol level by the Internet Engineering Task Force, IETF. The WebRTC mission, according to WebRTC.org, is to enable rich, high-quality RTC applications to be developed for the browser, mobile platforms, and IoT devices, and allow them to all communicate via a common set of protocols. The web has been successful partly because core technologies such as HTML, HTTP, and TCP/IP are open source and free to use. WebRTC joins this group by providing a free, high-quality, complete solution enabling communication in the browser. Using stun, ice turn, and RTP over TCP support for proxies, WebRTC contains key NAT and firewall traversal technology. History. In May 2010, Google bought Global IP Solutions, GIPS, a VoIP and video conferencing software company. GIPS had developed components needed for RTC like codecs and echo cancellation techniques. Google open-sourced the technology and engaged with W3C and the IETF to help standardize it for use by industry. In May 2011, Google releases an open-source project for browser-based RTC known as WebRTC. Work with the IETF has helped standardize protocols, and work with the W3C has helped develop the browser APIs. In May 2011, using a modified WebKit library, Ericsson Labs builds the first implementation of WebRTC. In October 2011, W3C publishes the first draft for WebRTC specifications. In February of 2013, WebRTC provided the world's first cross-browser video call. And in February 2014, WebRTC implemented the world's first cross-browser data transfer. WebRTC primarily functions through the use of three APIs. MediaStream, also called Get User Media, or GUM. MediaStream is used for the acquisition of audio and video streams. Combined with other APIs, GUM provides functionality. RTC Peer Connection. Calling RTC Peer Connection allows an application to establish peer-to-peer communication with another instance in another browser or other endpoint. Control messages called by a signaling protocol over a signaling channel is provided by unspecified means. Often this is by a script in the page via a server using maybe XML, HTTP requests, or WebSockets. Plugging GUM into RTC Peer Connection allows for the communication of audio and video data over a peer-to-peer connection. Two communicating peers both get their streams from GUM. RTC Peer Connection takes care of signal processing like noise reduction and also handles codecs. Methods are included that provide for peer-to-peer connections through NATs and firewalls. Security includes the encryption of audio, video, and other transmitted data. RTC peer connection also takes care of bandwidth management. All of its many features need only a few lines of code to be implemented for use by a web developer. RTC data channel provides communication of application data. RTC data channel is used with RTC peer connection. Developers can choose TCP or UDP, reliable or unreliable versions. RTC data channel features ultra-low latency and can even be used for file sharing. An example of this is sharedrop.io, where users can share files with each other directly without the need for the data to ever touch a central server. This API is intentionally similar to the WebSocket API to facilitate the same programming model. General architecture. WebRTC relies on abstract signaling to exchange session description objects between peers. A server is needed to set up a peer-to-peer route. Dynamic jitter buffers and error concealment techniques are included for audio and video, which help mitigate the effects of packet loss and unreliable networks. Also included are components for establishing a peer-to-peer connection using ICE, stun, turn, RTP over TCP, and support for proxies. For private IP addresses, WebRTC relies on stun and turn servers. A stun server is used to find initial addresses located behind NAT. Occasionally, when stun doesn't work, turn is utilized instead, which uses server bandwidth to relay data. ICE is the architecture that handles this choice for the user. Google has a public stun server that people can use. They also provide source code so that organizations can set up their own turn servers, which is originally described in RFC 5766. RFC 7874, WebRTC audio codec and processing requirements. This outlines some of WebRTC's audio and codec considerations. WebRTC utilizes both noise reduction and acoustic echo cancellation to improve the quality of audio streams. It also includes automatic gain control, noise suppression, and hardware access and control across multiple platforms. For video, the WebRTC project builds on the VP8 codec introduced in 2010 as part of the WebM project. It includes components to conceal packet loss and clean up noisy images, as well as capture and playback capabilities across multiple platforms. WebRTC consists of two distinct layers. Number one is the Web API, which we can see in this diagram in purple. This API is used by third-party developers to develop web-based applications like video chat. Number two, the WebRTC native C++ API in blue. This API allows browser developers to easily implement the Web API in their browsers. Session management. Abstract session layer allows for call setup and management. Actual protocol implementation decisions are left up to application developers. On the left, in the bottom left-hand corner, we have the voice engine. This is the framework for the audio media chain from sound card to the network. ISAC is a wideband and super wideband audio codec for voice over IP and audio streaming. It uses 16 kHz or 32 kHz sampling frequency with an adaptive and variable bit rate of 12 to 52 kilobits per second. ILBC is a narrowband speech codec for VoIP and streaming audio. It uses 8 kHz sampling frequency with a bit rate of 15.2 kilobits per second for 20 millisecond frames and 13.33 kilobits per second for 30 millisecond frames. ILBC is defined by IETF RFCs 3951 and 3952. Opus supports constant and variable bitrate encoding from 6 kilobits per second to 510 kilobits per second. Frame sizes from 2.5 milliseconds to 60 milliseconds, and various sampling rates from 8 kHz with a 4 kHz bandwidth to 48 kHz with 20 kHz bandwidth, where the entire hearing range of the human auditory system can be reproduced. Net EQ is for voice. It features a dynamic jitter buffer and error concealment algorithm used for concealing the negative effects of network jitter and packet loss. This keeps latency as low as possible while maintaining the highest voice quality. Acoustic echo canceller, software-based signal processing. In real time, it removes acoustic echo. Similarly, noise reduction removes background noise associated with VoIP like hiss, fan noise, etc. For a video engine, framework video media chain for video, camera to network, and network to screen. WebRTC uses VP8, which is a video codec from the WebM project. This is designed for low latency, which makes it well suited to RTC. Video jitter buffer. Dynamic jitter buffer for video to help conceal the effects of jitter and packet loss on overall video quality. Image enhancements. An example of this is in removing noise from the image capture by the webcam. In the transport section, we have the RTP stack, which is a network stack for RTP, the real-time protocol. Stun and ICE are used to establish peer-to-peer connections across various different types of networks. Peer5 is a startup that provides video streaming solutions that utilize WebRTC. Their product is being used presently by Dailymotion, among others, and it offers increased video quality as a result of offloading up to 98% of a server's CDN bandwidth by turning users into a peer-to-peer network that scales with demand. This is from their website. Peer5 operates the world's largest peer-to-peer content delivery network. We believe that the only way to make streaming video as scalable as broadcast television, able to reach hundreds of millions or billions of simultaneous viewers, is to employ a P2P architecture that enables streaming capacity to grow proportionally with streaming demand. A WebRTC gateway mediates between WebRTC and SIP. A WebRTC gateway also enables communication between a WebRTC phone and a VoIP or PSTN phone. The gateway extends the scope of WebRTC applications. Browsers using different applications can communicate with each other. Each browser-based client must signal to its server using proprietary application protocols built on top of HTTP and WebSocket. The WebRTC gateway decides whether a call is reachable with WebRTC, and if not, then the call will be translated into SIP by mapping different layers. Signaling. No standardized signaling protocol for WebRTC exists, so SIP and WebSockets are often used. The gateway repackages SIP packets from the WebSocket layer into UDP, TCP, or TLS. Media transport. For security, WebRTC specifies that applications must use SRTP for transporting media content. Not all VoIP apps support SRTP. In this case, the gateway maps between SRTP and RTP. Media content. WebRTC specifies that applications must use either G711 or Opus for an audio codec. Applications using SIP may use other codecs. The gateway translates between WebRTC and SIP sides of this conversation. Media address negotiation. WebRTC uses stun and ICE to traverse NAT and exchange media packets. SIP may not support ICE, so a gateway will act as an ICE endpoint and route media packets. WebRTC gateways are often integrated into SBC's session border controllers provided by SBC vendors. Some functionality like media handling and signal mapping is already supported by SBC. Open source WebRTC gateways include OverSIP, Reciprocate, WebRTC 2SIP, and FreeSwitch. There are also many commercial solutions available. Okay, so this is the demo portion of this presentation and is part of the code lab presented on WebRTC.org. What we are doing with this demo is creating a web app that can access your computer's web camera, take a photo, then send that photo to another user peer-to-peer without the need for the data to go through a central server. So first of all, I have installed Node.js. I run node index.js from the root folder of my project, which can be found on my GitHub page. Once we have Node.js running, we can navigate to localhost 8080 and we ask for permission by our browser, Brave of course, to give this page access to the camera. An ID is produced here for this session and it is located in the URL, which we can then copy and paste into another window to start a peer-to-peer connection. So this is what we see from the first web page. The first screenshot is what I see on the first page before I call RTC peer connection by opening a second page. The second screenshot is what we see on the first page after creating the connection. If I press the button labeled snap and send, then it should send a copy to the second web page I opened. Voila, you can see that the photo that I have sent has been received successfully. If we look at the console and the Brave developer tools, we can get a good idea of how this is all working. This is from the second peer that I started. On the first line it says request to join room. The first client was client 0, so this is client 1. If we scroll down, we can see what methods are being called. After we join the room and the peers are introduced to each other, get user media is called to connect the webcam. Session descriptions are exchanged. RTC peer connection is called using ICE so that direct peer-to-peer capabilities are now established, and near the bottom of this page you can see that an RTC data channel has been created to allow the picture data to be exchanged. In this screenshot we can see that our picture is roughly 1.2 megabytes in size, and it will be sent in chunks and then checked to make sure that they are all delivered properly. Finally, as we can see on the bottom of this screenshot, the photo is rendered. This ends my presentation on WebRTC. I hope you enjoyed it and learned something along the way. Thank you.